expression for back EMF in synchronous motor. So here objectives are derivation of expressions for back EMF, problems on back EMF equations. So back EMF and load angle. Here in case 1 the power factor is lagging, that means here under excitation, so EB less than V, EB less than V. So now next V is supply voltage, that is in per phase, and AB is back or induced EMF per phase. So now IA is armature current, it is in per phase manner. So next one is here impedance drop per phase, ER is equal to IAZS, and the power factor angle, so pi, that is power factor angle, and alpha is nothing but it is load angle, it is load angle. Theta is nothing but internal angle or tan inverse x by RA. So now see here, applying cosine rule to, so triangle OAB, OAB, so OA is red mark and OB is, so it is yellow mark, not yellow mark, it is a just a green type, and BA is the black color mark. Figure the current armature IA is lagging with angle of pi, so behind that applied voltage V, and V and AB, which results gives that ER, that is, so that is the resultant voltage. Now the angle between ER and IA is theta, that is internal angle or impedance angle. Pi is phase angle, alpha is load angle. Now here EB square, that is nothing but V square plus ER square minus 2V ER cos theta minus pi. So now AB is equal to under root of V square plus ER square minus 2V ER cos theta minus pi. So now back EMF and load angle. Here in this case, so in this case that is nothing but EB by sin theta minus pi is equal to ER by sin alpha. So AB by sine rule we can write here EB, that means back EMF, by sin theta minus pi, sin theta minus pi, that is equal to ER by sin alpha. That is the sine rule applied. Now here the sine alpha is nothing but sine alpha is equal to E or sine theta minus pi divided by EB. So hence the load angle alpha can be calculated once EB is known. Hence the load angle alpha can be calculated once EB is known. So now in case 2, what is the back EMF equation in case 2? The load angle. Here the power factor in case 2, the power factor is leading. That means over excitation. Here AB is greater than V. So see here applying cosine rule. Here the current is leading with pi angle. So observe this one, very important in the phasor diagram. So here voltage V and the current is leading with pi angle. So and ER is theta plus pi. ER is theta plus pi between the V and ER, and here EV is greater than V. So now AB square is equal to V square plus ER square minus 2V ER cos theta plus pi. So now AB is equal to under root of V square plus ER square minus 2V ER cos theta plus pi. So this is the so back EMF formula in leading or over excitation cases. So now next to go for here EB by sin theta plus pi is equal to ER by sin alpha. Here see observe this one. So now sin alpha is equal to ER sin theta plus pi by AB. So now hence the load angle alpha can be calculated once EB is known. Next, in third case, see observe this one. Here pi is 0. Why? The voltage and current, armature current, both are in phase. So here pi is 0. VA, IA are in phase. The resultant voltage is a combination of EB and V. ER is EB and V. And here theta is between the ER and IA. This is the phasor diagram. From this phasor diagram we can calculate. So we can calculate the back EMF. Now EB is equal to V here, that means it is normal excitation. Applying cosine rule to triangle OAB, here AB square is equal to V square plus R square minus 2VER cos theta. So this is the EB is equal to under root of V square plus ER square minus 2VER cos theta under root. This is the formula for back EMF. So here applying cosine rule to the load angle in unity power factor RAB is equal to be under normal excitation. So here EB by sin theta is equal to ER by sin alpha. So once sin alpha is nothing but here ER sin theta by AB. So now next one here, when we know the hence the load angle alpha can be calculated once EB is known. So that is the formula for the sin alpha. Now problems, we go for problems, small example problems, we have to do that. So here, so once again read it. So a 400 volts 3-phase star connected synchronous motor has a resistance of 0.3 ohms per phase and synchronous reactance of 2.4 ohms per phase. The motor is operating at 0.8 power factor leading, taking a line current 80 amps. Determine the value of generated EMF per phase and also its line current. They are asking generated EMF and current. Now solution is this 3-phase star connected synchronous motor. Now the supply voltage VL is 400 volts and the phase voltage is the line voltage by root 3, that gives the 231 volts, and armature resistance RA is 0.3 ohms per phase and XL is, that means synchronous reactance XS is 2.4 ohms per phase. Here these are the given data and power factor also given, that is cos pi is equal to 0.8 leading. So here from these data we have to solve the problem. Now pi is equal to cos inverse 0.8, that gives the 36 degrees, so 87 minutes. Now here the phasor diagram for leading power factor, her voltage and current between these phase angle is pi, that is leading, and the internal angle theta is between the ER and IA, that is internal angle or impedance angle, and alpha is load angle. So now here line current IL is equal to 80 amps and star connection the phase current is equal to line current. Now in armature current the per phase is IA is equal to I phase. So here the armature current also same phase current, that is nothing but a line current in star connected. Now theta is equal to here impedance angle theta is equal to tan inverse XS by RA. So that is that impedance angle, that is equal to tan inverse of, so 2.4 by 0.3, it will give the 8.7 degrees, that is the impedance angle 82.7, and therefore theta plus pi is nothing but 82.7 plus 36.87, that is gives the 119.7 degrees. Here synchronous impedance is Zs is equal to under root or A square plus X square. So by substituting RA and XS we get the Zs Here under root of 0.3 square plus 2.4 square, that gives the 2.42 ohms for phase. That is called synchronous impedance. Here ZS is the 2.42 ohms for phase. Now impedance drop for phase. Impedance voltage drop. Impedance drop means here impedance voltage drop per phase is IAZS. IA is how much they given 80 and ZS is 2.42. So now this current into this synchronous impedance multiply, which gives that the voltage drop in impedance. So now here 80 is multiplied with 2.42, which gives the 193.6 volts. So this is the impedance drop voltage. 193.6 is impedance drop voltage. Now next one is from the phasor diagram generated EMF, that is EB. What is the formula for leading cases? Here EB is equal to V square plus ER square minus 2 VER cos cos theta plus phi. Here this is for the leading power factor. Now here EB is equal to under root of V is 231 and ER is 193.6. So here EB is equal under root of 231 square plus 193.6 square minus 2 into 231 into 193.6 into cos 119.74, that is 367.7 volts. So back EMF is, so here generated EMF is for phase is 367.7 volts. This is the voltage developed in the armature, and that is called back EMF. Here the back EMF is more than that of supply voltage, that is this is nothing but a over excitation. Here from this concept we know that by observing these values EB and V, we know that this is over excitation. So line voltage is EB is equal to root 3 into 361.7, that is 636.87 volts. So now this next, now go for the problem number 2. A 10 HP 400 volts 3-phase star connected synchronous motor has a synchronous impedance per phase of 0.35 plus J 2.8 ohms. Find the induced EMF, line value, and the angle of retardation to which the motor be excited to give a full load output at 0.866 leading power factor. Assume an efficiency of 88%. Now go for phasor diagram. We know already, we see in this already. So IA is leading and 3-phase star connected synchronous motor, and output is, it is in HP. So you will get into convert into watts, that is 10 into 73.5, which gives the 7355 watts. Now supply voltage is, it is line voltage 400 volts and voltage for phase V is equal to 400 by root 3, that is equal to 231 volts. Now so here the efficiency is 88%, the value is nothing but 0.88, power factor is 0.86 leading, pi is 30 degrees, and input power is equal to output by efficiency. Here input power is nothing but output by efficiency. What is that output? Here it is mechanical output, that is 73.55 watts, by 0.88, which gives you 8357.95 watts. Here this is the input power. Now input power is equal to root 3 VL IL cos phi. What about the line current? IL is equal power by root 3 VL cos phi. Now here by substituting those values in this line current equation, so 8351.95 by under root 3 into 400 into 0.866, that is 13.93 amps, that is the line current or phase current in star connected. Now next, for star connection, IL is equal to I phase, that is equal to IA, that is nothing but 13.93 amps. Now synchronous impedance ZS is 0.35 plus J 2.8 ohms per phase. Now ZS is equal under root of 0.35 whole square plus 2.8 whole square, that is equal to 2.822 ohms per phase. Now theta is equal tan inverse of 2.8 by 0.35, that is 802.87 degrees. Theta plus phi is nothing but 112.87. Now next, resultant voltage GR is equal to IA into ZS, that is equal to 13.93 into 2.822, that is equal to 39.31 volts. Here from the phasor diagram, by cosine rule, EB for phase is equal to under root of V square plus ER square minus 2V ER cos phi. So here AB is equal to under root of 231 square plus 39.31 square minus 2 into 231 into 39.31 cos of 112.87, which gives the 248.93 volts. The line value of EB is equal to root 3 into 248.93 volts. Now by sine rule applying, so EB by sine theta plus phi is equal to ER by sine alpha. Now sin alpha is equal to ER sin theta plus phi by EB, that is equal to ER is 39.31 sin of 112.87 divided by 248.93, so which is gives the 0.1455, that is sin alpha. Alpha is equal to sin inverse of 0.1455. The angle of retardation is alpha, that is 8.37. Next problem. A 3-phase 440 volts 50 Hz star connected synchronous motor develops 7.46 kilowatts. The effective armature resistance per phase is 0.5 ohms. The motor operates at a power factor of 0.75 lagging. Stop. Iron and friction losses are 1350 watts. Calculate the armature current, the power input and efficiency of the motor. Here the solution is given. See here, this is the 3-phase star connected motor and line voltage is 2000 volts and per phase is by root 3, which gives the 1154.7. RA is equal to 0.02 ohms per phase, XS is equal to 2.2 ohms per phase. Now theta is equal to tan inverse of XS by RA, that is equal to tan inverse of 2.2 by 0.2, that is gives the 84.81. Induced EMF, that is equal to 2500 volts. Now phase induced EMF voltage is 2500 volts by root 3, that is 1443.4 volts. Now solution, as EB is greater than V, the power factor is leading, current leads the voltage by an angle of pi. Let IA is divided into two components, that is active component IA cos phi, that is I1, and reactive component of current I2, that is IS sin pi. Now this IA is IA cos phi plus J into IS sin pi. So I1 plus Ji2. So input power is equal to 8 P is equal to 800 kilowatts, that is 800 into 1000 watts. Now the power is equal to root 3 VLIL cos pi is input power. Here for star connection, the line current IL is equal to I phase IA, that is nothing but I1 is equal to IA cos pi, that is nothing but 800 into 1000 by root 3 into 2000, that is nothing but 230.94 I1. Here ER is equal to IA into ZS, that is nothing but I1 plus JI2 to RA plus JXS. Here I1 is 230.94 plus JI2 into 0.2 plus J2.2. So here 46.188 plus J508.07 plus J0.28 minus 2.2 I2, that is 46.188 minus 2.288 plus J508.07 plus 0.212. So 46 finally 46.188 minus 2.282 plus J0.8.7 plus 2.28. The phasor diagram is, so already we know that the phasor diagram. Theta pi alpha. From the figure, phasor diagram is Y is equal to V, that is nothing but 1154.7 volts, that is A1. AB is equal to EB, that is nothing but 1143.4 volts. OB is equal to AR, that is nothing but OC, that is OC is nothing but 46.188 minus 2.2I2, and BC is 508.7 plus 0.282. From a triangle ABC, AB square is called A square plus BC square, that is nothing but A square plus BC square plus BC square. Here from the calculations we get the I2 is equal to 106 amps. I2 is equal to 106 amps. For star connection, we get IAL is equal to IA, that is I1 plus JI2, that is 230.94 plus J106. Here we get finally the value is 254.1 amps. Current is 254.1 amps. Now power factor is nothing but cos pi IA cos pi by IA, that is I1 by IA. Here 230 by 0.94 by 254.1, which gives the power factor 0.91 leading. This is the problem is completed. Now